In section 9.4, we are looking at derivative formulas. And before I actually state the first formula, I want you to look at some examples of derivatives. If f of x is x squared, then f prime, the derivative, is 2x. If f of x is x to the third, then f prime of x is 3x squared. If f of x is x to the fourth, then f prime of x is 4x cubed. If f of x is x to the 10th, then f prime of x is 10x to the 9th. If f of x is x to the 32nd, then f prime of x is 32x to the 31st. Look at the original function and then look at the derivatives. See if you see a pattern in what happened here. Hopefully, you noticed that when we wrote the derivative, we took the old power and dropped it to the front, and then the new power went down by 1. This is called the power of x rule for derivatives. The formal statement for the power of x rule, if f of x equals x to the n, then f prime of x, its derivative, equals n times x to the new power of n minus 1. I want to look at the idea of the function f of x equals x, and we want to find the derivative for this function. If we follow our derivative rules, then f prime of x will equal the old power there is 1, x to the 1 minus 1 is 0. But anything to the 0 power is 1, so the derivative of x to the first is 1. Now I want to think about a function like f of x equals 3. Think about what the graph of f of x equals 3 or y equals 3 is. The graph of that function is a horizontal line. And when we are finding derivatives, we are finding the rate of change for a horizontal line. So, how much does a horizontal line change? How much does its slope change? It has no change. The slope stays constant. So the derivative of 3 is 0. There's no change in that function. And this would be true for any constant because the derivative of any constant is a horizontal line. So in calculus notation for those two rules we just did, if your original function is x, then the derivative will be 1. If your original function is a constant, which we represent by the letter c, then your derivative will be 0. Now that we have learned our first couple of rules, we are going to practice finding some derivatives. And on A, the function we are given is y equals x to the 16th. Using our rules, then, y prime, drop the old power to the front, 16, x, 16 minus 1 is 15. And there's your answer. When you have a problem like example B, where the function is 1 over x to the 6th, what you need to remember is that our power rule only works when the x is in the numerator. So this is going to call back some algebra skills for you. When you take a power of x and move it to the numerator of the fraction, remember that that changes the sign of the exponent. So 1 over x to the sixth is equal to x to the negative sixth. Now that the function is in the proper format, we can do the derivative. So the derivative of this function, f prime, drop the current power to the front, negative 6x. Now be careful, because if you do negative 6 minus 1, you go to negative 7. Be really careful on your subtraction. It's a very, very common mistake for students to make. On our next example, our given function is x to the 7/2, and this is already in the correct format. The reason that I want to do this example is because you will frequently have fractional exponents that you have to do a derivative with. So you have to be able to subtract with fractions. So if we want to do this derivative, remember that the power goes down to the front, the original power. So we now have 7/2 x. We need to do 7/2 minus 1. If you make 1 into something over 2, get a common denominator, it has to be 2 over 2. If we take 7/2 minus 2/2, we are going to get 5/2. The next rule that we need to look at is called the constant times a function rule. If you have f of x equals k, some constant, 3, 5, 12, whatever, 1/2, times a function of x, then the derivative of that, f prime, notice that you keep k. You keep the coefficient, whatever it is, and take that times the derivative of your function. Let's put this new rule into practice. So we are going to find the derivative. In our first example, we have f of x equals 3 times the function x to the 8th. What this rule that we just looked at tells us is that when we do this derivative, that we keep the coefficient and then do the derivative of the function of x. Well, from doing our power rule, that will be 8x to the 7th. Now multiply the 3 times the 8 and you get 24x to the 7. On B, our function is y equals x to the 6th over 3. The first thing that you need to recognize about this is that it could be rewritten as 1/3 times x to the 6th. Those two statements are equivalent to each other. So if we put our rule into play here, we are going to keep the coefficient 1/3 and then do our derivative of the x term, which will be 6x to the 5th. If you take 1/3 times 6, what do you get? You get 2x to the 5th. So notice on both of these examples that the answer that we got when we were finally done, up on A it was 24 and on B it was 2, is the same as if we had just taken our power times our coefficient right off the bat. If we had just taken the power times the coefficient right off the bat, we would get 24. Power times coefficient, we would get 2. So you can skip this first step where we wrote out the constant, the coefficient, times the power. You can skip those steps and go straight to the answer. On example C, we have y equals 3 over 5x to the 2nd. Let me rewrite this a little bit to help you see what's going on. We could rewrite this to be 3/5 times 1 over x squared. Those two things are equivalent to each other. And remember that in order to use our power rule, x squared needs to be in the numerator. So we are going to rewrite it one more time as 3/5. Now if I move that to the numerator, it becomes x to the negative 2. Now we are in the proper format to use our rules. So let's do the derivative. Thinking back to what we just said, you can just take the power times the coefficient. If I take negative 2 times 3/5, I will get negative 6 over 5. Keep your x. Now do negative 2 minus 1, which puts you at negative 3. You may leave your answer in that format with the negative exponent. That is absolutely fine. But just so you recognize, this could then be rewritten as negative 6/5 times 1 over x to the positive 3, which would be negative 6 over 5x to the positive 3. You do not have to go all the way to this last step. I just want you to recognize how these things might be written. On example D, our function is 8 over x to the 3/5. Recognize that this is the same thing as having 8 times 1 over x to the 3/5. And then if we move that to the numerator, it becomes 8 times x to the negative 3/5. Now we're in the correct format to use our power rule. And so we are going to drop and take the power times the coefficient, which is going to give us negative 24/5 x to the, now we need to take negative 3/5 minus 1, which would be the same thing as having negative 3/5 minus 5/5. That's going to give us negative 8/5. So this is our derivative. Our sum and difference rules tells us if we have some given function that is made up of individual functions u and v that are being added or subtracted, then the derivative of the entire function is the same thing as doing the derivative of each term. Let's practice doing the sum and difference rule. We are asked to find the derivative for f of x equals 3x to the 5th plus 7x cubed minus 10. The sum and difference rule says just do the derivative of each term. So the derivative of our main function will be the derivative of each term. On the first term, we're going to take 3 times 5 and get 15. X, go down by 1, 4. Plus, on the second term, take 7 times 3, get 21. X, go down by 1, 2. And remember that we said that the derivative of any constant is 0. So you do not have to have the 0 on the end. Your derivative would be 15x to the 4th plus 21x squared. On example B, we are given a function named y with the first term x to the 7th minus 4x to the 1/2 plus 3x to the negative 3 plus 7. Doing the derivative of each individual term, for the first term, we're going to drop the 7 and then go down by 1, so we'll have 7x to the 6th. Minus. On the second term, we're going to take 1/2 times 4, which is 2, x to the, now think about what we're doing here. We're doing 1/2 minus 1, which is negative 1/2. So the exponent on term 2 will be negative 1/2 plus, on the next term, we're going to drop the -3 and take it times 3 and get -9x. -3 minus 1 gives me -4. And then the derivative of 7 is 0. So we can write this as 7x to the 6th minus 2x to the -1/2 minus 9x to the -4, and then we don't need to write the 0. Now that we know how to do our derivative rules, we are going to put these into practice in some application problems. Our first example tells us that the position function of a particle is f of x equals 100 plus 160x minus 16x squared, where x is the time. And we are asked to find the velocity function and the velocity at x equals 0 and x equals 3. So we actually have two questions here. Question 1 says, find the velocity function. It's kind of three questions. And then we have find the velocity at 0 and find the velocity at 3. So our first chore is to find the velocity function. The velocity function is the derivative. Remember, as soon as you see velocity, the word velocity, that tells you you want the derivative. What's the derivative of 100? The derivative of any constant is 0. So we're not going to write that term. The derivative of 160x. Remember, we keep the coefficient, and we said earlier that the derivative of x to the first is just 1. So it would be 160 times 1, which is 160. Minus, drop the 2 times the 16, you're going to get 32x. So there is your velocity function. So this is question 1. Question 2 says, find the velocity at 0. So the velocity at 0 will be 160 minus 32 times 0, which is 160. We don't know any units of measure here, so we can't put a label on there. What we do know, though, is that we are moving forward and increasing by 160 whatevers from time 0 to time 1. So there's the end of question 2. Now for question 3, we want to find the velocity at 3. Well, this will be 160 minus 32 times 3. And this gives us 160 minus 96. And 160 minus 96 is 64. And so this is your answer for question 3. Again, because this is positive, we know we are increasing and moving forward at 64 whatevers. We don't have a label from time 3 to time 4. Question B asks us to find the time or times when velocity equals 0. When you have a problem like this, you take your velocity function, which in our problem was 160 minus 32x, and set it equal to 0. So we're going to do 0 equals 160 minus 32x. We're going to add 32x to both sides and get 32x equals 160. Divide both sides by 32 and we get x equals 5. So there is only one time when velocity equals 0, and that is at 5. On example 5, the equation of a function is given by f of x equals x cubed minus 3x squared plus 5. Question A says to find the formula for slope of the tangent. Anytime you see the phrase slope of a tangent, that's telling you you need to find the derivative. So we're going to find the derivative of our function. Take the 3 to the front, 3x, go down by 1 squared, minus, take the 2 times the 3 and get 6x, go down by 1 to the first, and then the derivative of 5 is 0, so we don't need to write that down. So this is the formula for slope of the tangent. Question B says to find the equation of the tangent line at x equals 1. Anytime you need the equation of a line, you need a point and the slope. And when we look at our information, we only have the x value. So we need to find the y value. If you ever need to find a y value, you must put the x value into the original. So y equals 1 to the third minus 3 times 1 squared plus 5, which gives us 1 minus 3 plus 5, which gives us 3. So our point then is 1, 3. Since we have the point, now we need the slope. And if it's slope of a tangent line, then we need to use the derivative. So the slope of the tangent at x equals 1, we're going to put 1 into the derivative, which is going to give us 3 times 1 squared minus 6 times 1, which gives us negative 3. Now we have our point and we have the slope, so we are ready to use the point slope formula, which is y minus y1 equals m times x minus x1, where the y stays in as the variable, y1 is the y of your point, which is 3. We just said slope was negative 3 times x minus the x of your point is 1. Now let's do our algebra here. So we have y minus 3 equals negative 3x plus 3. And then add 3 to both sides to solve for y. And we have y equals negative 3x plus 6. So this is now the equation of the tangent line at the point x equals 1. This picture is the graph of our original function x cubed minus 3x squared plus 5. And the reason that I put it in here is because I wanted you to see what we just found. Remember that we were using the x value of 1. At our x value of 1, if you go up and find the point, here's the point where x is 1. Is our y value 3 like we got? Yeah. And what we were finding then is the slope of this tangent line right at where x equals 1. We found the slope of the tangent line to be negative 3. Is that line going downhill? Yeah. And then the other thing is the equation of that tangent line would be negative 3x plus 6. That was what we found by doing question B. Question C asks us to find the value or values of x where the tangent line is horizontal. Before we start trying to work the problem, we need to remember what it means for a line to be horizontal. Any horizontal line has a slope of 0. So if you want to find where the tangent is horizontal, then you want to find where the slope of the tangent equals 0. What did we say the slope of the tangent was? It was the derivative. So in other words, you are finding where the derivative, f prime or y prime, whatever your name is, equals 0. Our derivative was 3x squared minus 6x. So we're going to set that equal to 0. To solve a problem like this, notice that we have a common factor of x. So we are going to factor out x, and that would leave 3x minus 6 inside. Now set each of those factors equal to 0. You get x equals 0. Set 3x minus 6 equal to 0 and solve that. You're going to get 3x equals 6. Divide by 3, you get x equals 2. So we now have two x values where our tangent is horizontal. Going back to our graph of this function, I want you to see at x equals 0 and x equals 2 what's important about those values. Notice that at x equals 0, you have a peak, and at x equals 2, you have a valley. A peak and a valley mathematically are called a turn. So what you have going here is a turn at both of those values, and that's where your tangents are horizontal. And that's something we will use as we move forward, so I just wanted to show you why that's important.